Okay, I just want to explain the twin paradox again using the normal mathematics and see how it relates to the mathematics that I'm using. So let's say that this is Alice, and he leaves Alice, and then he comes back to Alice. So this is Alice again when he comes back. Okay, but this is not distorted. So so you can think of that as Earth or something, and you can think of that length, which is gamma, as Bob's spaceship, and you can think of this as Bob's spaceship returning, and of course that length is gamma, that length is gamma, that length is 1, and that length is 1. So Alice simultaneously measures the length of Bob's spaceship as it goes whizzing by, and I'm using a B value of 0.6, by the way, and L0 is going to be 1, but she measures this distance between the front and back of the ship. Maybe something gets triggered on the front and the back, and then the light signals get sent out and she receives them simultaneously, and so she sees that that's 0 time there and that's 0 time there, but she knows that according to Bob, from her point of view, his ship is really longer than that because she's measuring a space contracted length. So she knows that this would have to be the synchronized 0 time in his frame there. Okay, so you've got your 3 zeros. Now finish the relativistic slide rule. It turns out that according to him, her universe or Earth is contracted to a length of L, which is here L and L, and she's heading past him in the opposite direction, so down. She's heading down in both cases here, whereas he's heading up the page in both cases here. So according to him, if she synchronized the clock at the front of his spaceship here to be 0, then at this point, which is her front of the ship point, time must have passed, so this must be positive. The clock here must have moved ahead, and in this case the clock hasn't even, in her frame, she's measuring the back of the spaceship here, calling that 0, but it hasn't got to the back of the spaceship in his frame, so he would say that this clock is behind in time, because it's going to get to 0 when it gets to the back of the spaceship, just as in this case it's going to get to 0 when it gets to the front of the spaceship. So this clock is ahead and this clock is behind. And so how do we calculate it? Well, in terms of distance, I'll just say what the relativistic slide rule would say. The difference in the distance between L and gamma is L over T squared, so that's a positive, and the difference in distance is, this time it's negative. This is space, the difference in the space. But in the difference in his time would be, in the top one it would be negative 1 over t, in the bottom one it would be positive 1 over t. But her time is time dilated, so the difference would be L over t, positive L over t for her, and negative L over t for her here when he's coming back. In other words, she's heading down, so he's seeing the front of her universe, Earth or whatever, as running slow, and therefore the rear clock is ahead in time. And in this case, he's actually seeing the rear as ahead, the rear of her universe as ahead in time. So that's always the case, that the rear clock is always ahead. But of course she's synchronized the two readings. So that's the reference we're using. So now to use the mathematics that is normally used, let's use the top one because that's the one I went with before. Let's say that she measures the length to be L0, and therefore the difference, and it's going to be this, which she calculates this way. She goes, she knows that the length of the ship in his frame is gamma times L0. By the way, L0 is 1, okay? But she knows, but her frame and his frame is L0 divided by gamma. Okay, so now you do some algebra. What you do is you factor out the gamma O squared, so that becomes 1 minus, and then you factored out that O0, so it's 1 at the top, and you also factored out a gamma from the top, which is equivalent to adding a gamma to the bottom, so you end up with 1 over gamma squared. And then 1 over gamma squared is the same as epsilon squared, and epsilon squared is just the square root of v squared, and just square it. And of course, if you square a square root, you just get 1 minus b squared, and 1 minus 1 is nothing, so you end up with a negative b squared, so you end up with a negative on the front, gamma L0 b squared. And remember that b is actually L over t according to relativistic slide rule. So you've got L squared over t squared times gamma, which is 1 over L, so you end up with negative L over t squared, which I'll put a different color just to point to these things, which I showed here. So that's the same calculation. But according to convert, this is according to Bob, but to convert that to time, you have velocity equals distance over time. You rearrange that, you get time equals distance over velocity. So you just got to divide out the velocity, which is b, so you end up with a negative gamma L0b, and that one, use a different color, that one is actually just L over t times gamma, which is 1 over L, and it just leaves you with this calculation here, 1 over t, and it's minus, so that's time. the difference in the time according to Bob. But what's the difference in the time according to Alice? We know that because of time dilation, he's going to have to divide that by gamma. So let me write it over here. So let's divide that by gamma, which basically just cancels out the gamma. So you end up with just negative L0b, and the L0 is 1, so you just end up with negative b, and get another colour, and that calculation is actually just negative L over t. So that's how it's normally calculated. And then you would, to calculate the positive values, you have to just make that L0 negative in the bottom one, and then you'll end up with positive values. Okay, so that takes care of that. I also wanted to look at the red shifts and the blue shifts. And so let's say that Alice is looking at Bob's ship go by past her, and she'll be looking at, I call it a yellow shift instead of a red shift because it's perpendicular and it's gamma. Okay, but if it's sort of whizzing sort of towards and past her, which is perpendicular towards, then I call that a green shift because it's L. So the light will be green shifted. Okay, and let's say that it's a parallel away. In other words, she's behind the ship and it's heading away from her. Then the difference will be, and just let me create a circle here, for 1 over t. Then the difference will be, she'll be getting gamma plus 1 over t. So this is it'll be redshifted by this amount. What she sees, the light from Bob's ship is heading parallel away. And let's say he's heading parallel towards her. That's going to be a blue shift, and it's actually that amount, which is gamma minus 1 over t. Okay, so they're the 4 types of blue shifts and red shifts. And I want to make one more interesting point, and that's, say this is just a quantum. Now, instead of spaceships and planets, I'm just talking about quantum particles. In that case, you sort of got the double slit experiment. The particles fight out of here. It doesn't, and then it just appears on the screen, say here, but it doesn't seem to take a path. It doesn't seem to travel. Unlike Bob, it just seems to go B in point A, and then it's at point B, and then it just seems to be some sort of superposition in the intervening time, which collapses. So let's look at these as just quantum particles. So Alice is just a quantum particle, and now Bob is just a quantum particle. So let's say he takes off from the particle detector, and because of his velocity, his length is going to be gamma, but he doesn't really have a velocity. He's actually just got this quantum particle has gone from here to here, and that distance, by the way, is 1 over L minus 1, and that's actually the reason for that calculation. When I want to say how far Bob travelled when he goes from, say, Earth to Alpha Centauri, it's because that's the displacement. So here I've got Bob. If I choose the middle of the circles, Bob actually went from here to here, and that distance is actually that. In other words, it's like you've got the superposition principle. You've got his initial location, then you've got his final location, and then the difference between those two locations is how you calculate the distance travelled. So that's interesting. Same, he's got an initial location and then a final location, and then the difference between those two locations, here's the middle of the circles, again is 1 over L minus 1. And so you add those two together and you get the total distance travelled. But anyway, this is like a superposition, isn't it?